Moving right along, problem 6 has this is where I start to get into the really freaky weird questions. So don't worry if these aren't immediately obvious to you. This is more, if you're still reading at this point, you should just be sort of enjoying the ride and seeing what you can learn from it. So I mean, if you can solve them, that's great. I encourage you to try, but don't feel like you're gonna screw up in the test if you can't get all these by yourself. So here's this big ramp with a mass m, and it's got this complicated shape. But we start this block of mass little m, a small block, at the top of this ramp, and it drops a height h. So I said delta h here, but I really mean it just goes from h down to 0. Okay, so it starts up here, and then at the bottom of the ramp it flies off horizontally. We want to find the speed of the block as it leaves the ramp. Okay, so the first we need to figure out what is true here. So the first thing is that momentum will be conserved. Or, sorry, momentum in the x direction will be conserved. Well, it's going to be constant, okay? Why is that? Well, if you look at this, you can see there's going to be like normal forces acting between these wheels and the things, and the wheel's going to be holding up, the thing. So there's going to be a force from the ground pushing up, but that's going to be a straight vertical force. There are not going to be any forces acting on this little block or the big ramp except their interaction. All the horizontal force, the only horizontal force between these two is going to be the interaction between each other. So that means momentum, since there's no forces acting in the x direction, there's no impulse in the x direction, which means momentum in the x direction is conserved. And since they start at rest, it's not too hard to see then that initial momentum is 0, so therefore final momentum is going to be 0. So actually I can back this up and simply say that total momentum in the x direction is going to be 0. Okay, now is anything else conserved? Well, let's see, is kinetic energy conserved? This is a frictionless ramp, right? This is frictionless here. It says it rolls freely across the level floor, so that's frictionless too. So in fact, yeah, there are no non-conservative forces. We've basically taken care of friction. Gravity is going to pull this thing down, so there's going to be a change in potential energy, and that's going to increase kinetic energy. But total energy in the system, total mechanical energy, is going to be conserved. So best way to say that is change in E mech is going to be 0. Okay, so I'm just going to draw a little schematic representation of the system. And so there's my little m block and my big M block, and then here's my little m block flying off the edge at some speed v final. It's going horizontally. The big M block is going to be moving this way. So I'm going to label this state 1 when the little m is at the top, and state 2 is when little m is at the bottom, just as it flies off. So in state 1, what's my potential energy? Whoops, sorry. What's my kinetic energy of the system? Well, that's going to be the kinetic energy of block 1, which is 0, plus the kinetic energy, or the little block, sorry, is what I meant by block 1. The little block isn't moving, big block isn't moving, so there's no kinetic energy in the system. Potential energy from gravity, I'm going to define this level here as my potential energy from gravity equals 0 spot, which means right here at 2, potential energy is going to be 0. At 1, we're a height h up above the 0 spot. So UG is going to equal m times g times h. Okay? And so total mechanical energy is going to equal mgh. Little m times g times h. Simple enough. Now at 2, this gets a little more tricky. Kinetic energy at 2 is going to equal the kinetic energy of this little block, which is going to be 1/2 little m v final squared, right? Plus, now we're getting interesting. 1/2 m. Okay, so plus the kinetic energy of the big block, which is going to be 1/2 big M times v. And I'm going to call that VR. So VR is going to be the velocity or the speed of this ramp. Okay, and yeah, you better believe this is getting interesting here. So, and then potential energy. I don't know why I said interesting, but anyway, so potential energy here is going to be 0. So that means total mechanical energy here is going to be 1/2 little m vf squared plus 1/2 capital M VR squared. And these two are going to be equal. Okay? So we can get an equation out of this, which is, of course, mgh equals 1/2, why not just collect, okay? So mv final squared, which is vf final of the little block, plus big M VR squared, which is velocity of the ramp. Okay, now, where does this leave us? This leaves us with two unknowns, this VR and this VF. We were given little m, big M, h, and we know g, and we know what 1/2 is. So, what's our other equation? Well, we just took advantage of this one, right? So, the other one we need to use is total momentum is going to equal, is going to still equal 0, even at the end. So, at point 1, we know total momentum is equal to 0, right? That's kind of obvious because nothing's moving. Okay? At point 2, total momentum in the x direction is going to equal, so let's see, we're going to have negative, this is going to be moving to the right, so we're going to have, well, we can just say, let's see, big M times V sub r plus little m times V sub f, and that's going to equal 0, right? This is going to be conserved. So what this means, let's solve this for V sub r. V sub r equals negative little m over big M times V sub f. And if we plug that in, it should work out to be 0. Right, okay. So, let's find out now. We want to get this into a state we can plug in here. So we can actually do V sub r squared, because it's V sub r squared here. So I'm just going to take this and square it. Okay, so this gives us V sub r squared equals little m squared over big M squared times V sub f squared. And so we're going to take, now, this is going to be tricky, so let's make sure we do it right. We need this equation and this equation, and we're going to plug this into there. So this goes into there. And so what that does for us then is we get, okay, so we get mgh equals 1/2 times little m vf squared, and this was little mgh because that's what's losing potential energy, plus, and then big M times this little m squared over big M squared. So this has come out to be little m squared over big M times vf squared. Okay, so now we've got it all in terms of vf squared. And so what we can do now is, let's see, I'm going to pull the 2 over, and I'm going to pull a little m. Actually, no, I'm just going to leave this as, so I'm going to pull an m out here. So equals m over 2 times vf squared. So that's, this term is a 1 plus little m over big M, and that's also vf squared. So this here is still equal to this, and it's all equal to this, right? Okay, then we're going to cancel, a little more cancellation. Cancel the m, and then we get the 2gh. So this is going to get us vf squared equals 2gh over 1 plus little m over capital M. And that should be good enough to get us an answer. I'm not gonna particularly care about getting the square root out. So what you can see here is if the more massive big M gets compared to little m, the smaller this part gets. And if little m over big M is tiny, 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 so it's basically 0, then this just turns into vf squared equals 2gh, which we've seen before. That's just what happens if you drop a block from, drop a block from some height. That gives you its speed when it reaches the bottom. So this all should make sense, but that's how you solve that one.